Hello, patient people. In this video, I'm going to talk about learning about a heat transfer mechanism and heat transfer, calculating thermal expansion, and solving calorimetry problems. Simply, if one object is given heat to the other, how their temperature changes. Thermal expansion is important for building bridges. For example, in the summer, bridges will be expanding, getting longer. In the winter, they will be contracting, getting smaller. We have to take that into account to be able to avoid a curving of the bridges. In 1800s, they built the railways and they didn't take into account of thermal expansion, and the railways all curved and became bad. So if you're an engineer building something involving materials, you need to take into account thermal expansion. Here you see a bridge, and these cracks here are letting the bridge expand and contract without causing it to curve and give trouble to people who are driving on it. How do we calculate thermal expansion? Is a simple equation. Here, as we see, we have delta L, which is the amount of expansion, a constant alpha times the initial length of the object times how much temperature change, delta T. So that gives us the amount of expansion. If we have a kind of 1D length, we can apply this to bridge, for example. Alpha here is called the expansion coefficient or coefficient of linear expansion. Simple as that. So if I have a bridge, let's say, it has an initial length of Li, then let's say it became summer and it expanded a little bit. Oops, let's try that again. So it became a bit larger. And the amount of expansion here is what is called delta L up there. And to calculate that, we multiply the initial length with an expansion coefficient related to material we have times how much temperature changed in the summer, delta T. This would be always, you guys know what delta is, change, so the final value minus initial value of the temperature. Similar approach applies to a volume. Volume will change, only the expansion coefficient will change, will be a different number. That's all. We'll say that it's expansion coefficient beta times initial volume times delta T will give us how much the volume changed. So if I have an initial volume here and it expands, we will have an extra volume, this guy getting a little bit larger. So delta V is how much larger it got, right? So I can calculate that. So the amount of expansion is just this extra volume we are getting here, right, on the sides. That's delta V. And that's how we calculate it. If I want to find the final volume, I have to add that delta V to initial volume. And I get to the final volume. Let's call it V final. The same goes for final length. The final length here would be all this length. It's obvious. Oops, what's going on here? Something is wrong with my device. All right, let's undo that. Final length would be initial length plus the delta L, right? Obvious. If I have a contraction, I will have smaller, right? If it's cold, I'll have smaller. So then delta L will be negative because final temperature will be smaller than initial. So you'll have a smaller length. That's the only difference there. We all know about thermal expansion. For example, quite often if we can't open a jar, what we do is we can keep it under hot water. The lid of the jar will expand more than the glass, the jar itself, because the material used to make the lid, it's generally aluminum or tin, and it expands more. It has a higher expansion coefficient, expands more than glass, and we can easily open it. Expansion coefficients depends on the material we have, and they are listed as the unit as Kelvin to -1. They are given for, well, linear for length and volume expansion coefficient. So they are given values depending on the material we have. Here is an example question. It tells us the height of a Space Needle, a steel observation tower in Seattle. I got a picture of it here. Is 180 meters in 0 degrees Celsius. So assume this is 0 degrees Celsius, and we have a length. That will be our L initial. That should be the meter, right? So there's this guy over here. So the initial length is 180 meters, and the initial temperature is 0 centigrade degree. In a winter day, how much taller it is on a hot summer day. So if we have a hot summer day, the sky will be a bit larger. Let me draw it. I see it got a little bit larger. It became this large, right? It will have a final length. We can find that. Will be a little bit longer than the initial length, and we can find the amount of expansion using this delta L equation here. So this guy. So the question is only asking delta L, how much it expands, but let's find the final length as well. It's not a big stretch after that. Now in a hot summer day, temperature is 30 degree, given as 30 degrees, so T final is 30 degree here. Notice here I have alpha as Kelvin to -1, so I have to convert temperatures to Kelvin. Alpha for the steel, Space Needle is made out of steel, and alpha for the steel is given as 12 times 10 to -6 Kelvin to -1. I checked that from my table given here. Still, we're looking at linear expansion, how much longer the needle gets, so linear expansion coefficient. T final is equal to 30 degree centigrade, and we will convert to Kelvin here by just adding 273. Then it converts to Kelvin. So when we do that addition, we'll get 303, right? Yes. So this is 303 Kelvin. So centigrade to Kelvin, we say centigrade plus 73, and we convert it to Kelvin. We'll be using Kelvin still in this conversion. We'll be using all the time here in this section too. T initial is 0 degree plus 273. That will be 273 Kelvin, of course. Then I can directly find my delta T looking at 303 minus 273, 30 Kelvin. If I'm only looking at difference and converting only from Celsius to Kelvin, difference will become the same. But to be on the safe side, I will always convert. It doesn't work in all situations. If I only need delta T, it's fine. If I'm converting from Fahrenheit to Kelvin, for example, it's not gonna work. So I'm gonna keep converting. But for Celsius only, difference will stay the same here. Just note that. But I won't be dropping the conversion to keep that idea around for other types of questions. It does not always hold. All right, I'm gonna find now the amount of expansion. It's alpha L initial delta T My alpha is 12 times 10 to minus 6 Kelvin to minus 1. L initial was 180 meters. And delta T is 30 Kelvin. Notice how Kelvins cancels Kelvin and Kelvin to minus 1. So I'm going to get a meter here. Delta L will be a small number here. About 0.0648 meters. Meters to centimeters, remember, multiply by 100, so we move this 0.2 to the side. 6.48 centimeters. This might not be important for the snail to get larger or smaller in the summer or winter, but if this was a railroad, this would cause some curving and cause trouble in the trains to move on it. Anyways, that's our delta L. What is the L final? This is an expansion. I got a plus delta L here, increase, so I'll say initial plus that. And it will be 180 plus this much. How much is that? Let me quickly do that here. So 180. I don't want to do it in my head and make a small silly mistake here. 0.0648. Alright, that's what I thought. 180.068. Let's plus 0.0648. I'm going to complete this to 65 maybe. Let's do that actually. About 0.065. And we add them, we'll have 180.065 meters. A little bit of increase there. So that's thermal expansion. There isn't too much to it. Simple idea. We calculate the expansion, we add it to the initial value and see what is the final value. Volume is similar, only we use a different expansion coefficients. Applications as numbers. For example, very simple. Everyday uses when we measure temperature, outside temperature, room temperature in our room, we use thermometers. Thermometers works under the measuring of how much a liquid expands under heat, and then we have measurement points here showing how much delta T, calculating how much delta T would be. So mainly calculating using the idea that delta V beta, way initial, delta T, they give us what is the temperature outside, right? I'm just going to make up some values here, centigrade. So if this liquid expands this much, it's about 10 centigrade degree and so on. It's all calculated, set in the device. So we have, let's say this is 77 centigrade and so on. So the temperatures works under the idea of a gas or liquid expands under heat. In engineering, it's used in a very interesting fitting called shrink fitting. So they put two stuff together, one inside there that fits at cold. And then when you put these into a hot region, what will happen that they will expand, right? Everybody expands in the hot region. But if what I put inside the one part, so this guy goes inside this part, if this expands more than what is outside, this expands less, they will be stick together. So if I put them together in a cold temperature where generally is not a regular temperature, outside temperature, and then take them to an outside regular room temperature, they will fit without doing any welding and so on. And as long as it's not too cold, they will stay fit, which is a very interesting, nice idea there. Idea of expansion is also used in many other devices. For example, one very interesting idea is the automatic on and off switches we use for heat and water coffee makers and so on. The idea of putting two different metals together, here we have brass and steel, that has different expansion coefficients. So if they have same initial lengths, but when I heat them, one will have expansion coefficient alpha 1, L initial, 1 delta T. So if I hit them same amount of delta T, right? And one has a higher expansion coefficient than the other, it will be expanding more. So here, let's say L1, L initial 1 is the brass, and 2 as the steel. If I look at their expansion coefficient, brass has higher expansion coefficient. So if I heat the material, brass will be expanding more, steel will be expanding less. So maybe do it like smaller arrow. What will happen is brass will be larger. And if I make them cold, contraction also works the same. Brass will be contracting more and steel will be contracting less. So when I do this guy, brass is expanding. If I heat them, brass is expanding more, wants to get larger, but it stick to this steel, so it will curve over it. And if I make them cold, brass will shrink more, right? And the steel can't shrink as much enough. Then the steel will be larger, and then the curving will be to the side. How this works is we put brass, steel, metallic strip. When we hook up our coffee maker, let's say, they touch each other, they are straight when we just open it, when the water is cold. And this part is directly touching to water, as you see in this figure here. As the water heats, these guys also heats up, and they start expanding. But they curve like this because we have brass here, steel there, let's say, and brass expands more. So as the water reaches a certain temperature, they are set up in a certain way that exactly when the water starts boiling, this expansion is good enough so they're not touching each other here anymore. Electricity doesn't pass anymore from here to there. Here, electricity is passing. But here it can't, there's a break. So it turns off automatically. Brilliant idea here. One very interesting phenomenon that I want to talk about also in terms of expansion is the expansion of water. It's very different than any other regular expansion. Everything else expands when we heat it and keep heating, expands. At some point changes phase. We'll get to that. We take heat away, they contract, keep contracted. But that doesn't go for water. For water, if I look at a certain volume of water, for example, at a certain temperature, let's say I take it from a temperature 12 and it gets cold, I take heat away, it gets colder. What's happening here? It's shrinking, contracting, right? And it turns out that nature arranged it in a way that water contracts down to, as I go down to about 4 centigrade degree. And if it keeps getting colder and colder, it starts expanding. And because of that, when it freezes, ice has a larger volume, it will have a less density. We didn't get to density yet, but density is simply mass divided by the volume. We have the same amount of mass of water, it gets colder, it shrinks. Density gets higher because volume gets less at this part here. Then it starts increasing. Volume gets larger and larger. Remember again delta V, right? Alpha, beta. With initial delta T. Normally, the delta V is smaller and smaller, so final volume gets less and less until 0.4, but somehow after this point, volume gets expanding. We don't really understand why is that happening. And as volume expands, density, this rho is generally used for density, Greek letter rho. We can also call it D, but it's rho in the book, so I'll stick with rho. Density gets less. Again, we don't really understand why it deciding to expand after the 4 degree, but we understand why it is very important. out in the winter. We have lakes, we have marine life, and the marine life can survive because of this. As ice forms, it stays out on top of the water because it has less density than the water. It floats. And we have marine life continuing in the winter. That's a very interesting feature of water. Here you see water, ice. We all know that ice floats on top of water. This graph is showing the same idea, except in terms of temperature, density versus temperature. So as the temperature decreases, density increases up to 4 points because volume decreases. And then volume starts increasing, density starts decreasing. That's a very interesting phenomenon there. Another idea I want to talk about in this video is given heat to some objects, how much their temperature changes can be calculated as well using this equation here. Q here is heat. So let's say I'm heating some amount of water. M is the mass here. C is called specific heat. Each type of material will have different change of temperature. If I give them the same heat, this is temperature change, final temperature minus initial temperature. If I give the same heat to different materials, their temperature will change differently, even though they might have the same mass, because they will have different heat capacity. Those who has large heat capacity can take in a lot of heat without changing their temperature too much. If you look at here, heat is inversely proportional to directly proportional to heat capacity, So at larger heat capacity can take in a lot of heat without changing their temperature, which is why in the summer we might have hot air outside, very hot, we go swimming, we get into water is cool because water has a lot larger heat capacity than the air outside. I'm gonna move the sky a little bit. If you look at here, the heat capacity of water 4,190, larger than everything you see in here. Unit for heat capacity is joule per kilogram Kelvin. Because of that as well, at night when it gets cold, air gets cold out here, but water doesn't get cold as much. Now there is a heat taken away. Temperature changes a lot for air, not a lot for water. So very early in the morning we have cold air here. And then hotter water that can evaporate a little bit. But as the water evaporates a little bit, it condenses here. We have cold air. So very early in the morning, we see mist on top of lakes or rivers. It's a pretty cool thing to look at. That's because water has high heat capacity. Although temperature drops for air capacity, it doesn't drop for water as much. At the night, some heat is lost from the water. Also, the same heat is lost from the air because temperature drops. But temperature drops more significantly for air than water. So we have this nice phenomenon. In the morning, as the things are getting heat from the sun, inverse happens. Air heats up a lot, but water doesn't. That's why we have it as a cool. So high heat capacity is able to take in or give heat without changing their temperature too much. Two liquids A and B, we have a quick check here, have equal masses, equal initial temperatures. Each is heated for the same length of time over identical burners. That means they have each same Q given. Okay? They have equal masses but different heat capacity. Okay? Alright. So we heat them with the identical burners. We give them the same heat Q. They have the same mass. Afterwards, liquid A is hotter than liquid B. So let's say this is A. This is B. If I solve for delta T here, let me solve for it actually so we can mathematically also see this. It will be equal to Q over MC1, right? Let's call this delta T1. They don't have the same delta T's. B, delta T2 will be Q over MC2. After a while, we have seen that A is hotter. That means temperature of A, change of temperature for A is larger. I'm going to pick red here. Larger than B. So B is less than A. What does that mean? If this is larger than B, masses are the same, Q's are the same, that means the C, the capacity, heat capacity is less for A, more for B. So although T increases a lot for A, it doesn't increase for B as much. So which has the larger specific heat? Liquid B. Go back again. If the temperature is changing by a lot, while the Q's and masses are the same, means heat capacity is less for A and more for B. Alright, that's the heat capacity. Some nice simple plug and check questions like this one can arise. We have a 70 kilogram student. Catches a flu and his body temperature increases from 37, that would be my T initial, 37 centigrade degree to 39 centigrade degree. How much energy is required? Energy here is heat energy. Okay, in the context of heat, when we are asked how much energy is required, we talk about heat. Heat is a form of energy. This is a simple plug and chug question, calculating heat using MC delta T. We have to convert the temperatures to Kelvin. Again, for Celsius case, difference will stay the same because we're just adding 273 to both. But if I had Fahrenheit, that won't be the case. So I will still convert to keep the idea. So convert to Kelvin at 273 Kelvin. That will be 310 Kelvin here. 273 Kelvin, 312 Kelvin. That's right, great. All right. Mass is 70 kilogram. What is the specific heat? From our table, we can find the specific heat for a mammalian body to be 3400. So we'll use that. Unit is joule per kilogram Kelvin. And we'll calculate heat. Q is equal to MC delta T. Put in all the values. 70 kilogram is the mass. 3400 is the heat capacity. And delta T from here, let's directly find it. T final minus T initial will be 2 Kelvin. And once we do that, we'll find a large heat energy going into the body. 476,000 joules. That's it. Q is equal to MC delta T if a body temperature is increasing, and we can calculate it as so. Now, if there's phase change as we give heat to a system, something changes happens. Now I want to talk about that. We talked about solid, liquids, and gases already as the phases of matter. I want to tell you here, I got this picture from the internet and I was very happy to see that people are also teaching about plasma. So if I take something as solid, heat it up, it will become liquid, melt at some point, we know that, and heat and liquid, it will become gas. So over the heat, and what happens is molecules and atoms starts moving more and more, they separate more, become gas. If I keep heating a gas, mainly gas will become all ionized, meaning atoms will lose some electrons. Or if the heat is large enough, electrons, protons will just get out of the atoms and will flow around freely. That's what is called plasma. Now, why do we need to know about this? Our sun is actually made out of plasma. All the gases in there are ionized. We know there's hydrogen, helium, but they're all ionized. Hydrogen is actually, proton and electron are separate from each other. Proton is flowing around freely, electrons are flowing around freely. So all the stars are also plasma. That's just a side information. But phase change, when we keep heating objects that expands, at some point they change phase. We learned about as the objects are expanding, we have Q is equal to mc delta T. We learned about we can calculate the expansion. Let's do the volume expansion using a constant expansion coefficient, initial volume and delta T. What do we do if there's a phase change? Its solid will become a liquid become vapor, and so on. We will use different equations for heat. That's all we're going to do. So we'll talk about that now. Here I'm looking at ice. We take water from ice. Ice can be at 0 degree. Any degree lower than 0, it's still ice, right? So water, in terms of centigrade degree I'm talking about here, water is ice at 0 degree. And then if I heat the ice at 0 degree, it will start melting. Below 0, first I have to heat it up to 0 degree. So below 0, heat ice, it will stay as ice until the melting point, 0 degree, is reached. Then it starts melting. Okay? Keep heating up, it becomes all water. If I keep heating this water, it expands a little bit, stays as water. I keep heating until the boiling point is reached, which is 100 centigrade degree. Alright? And as it is boiling, it will be evaporating, becoming water vapor. Right? And it will all be water vapor at some point. Right? It will be all gas. Now, as this is happening, if I look at the temperature versus time, let's say I took that ice at minus 50 centigrade degree. I heat it up, its temperature will increase. The first section here. As I keep heating up and it's melting, temperature will stay constant because the heating energy, let's call this heat 1, heating energy I give to ice here is used for melting. So temperature doesn't change. It all melts, become all water. I keep heating up, now temperature will increase. Now I'm giving another amount of heat to water. It will increase in its temperature until the point of boiling is reached. Now boiling starts at 100 degree. As it is boiling, becomes water vapor, gas. Temperature doesn't change again. Alright? And then it keeps warming. After it becomes all water vapor, the temperature will change. When it starts becoming plasma, we are not going to look into that. A lot of different stuff happened there. Now the idea here is temperature changes while there is no phase change, and temperature stays constant although the material is taken in heat. I'm giving it heat. It's used for separating the molecules and melting or evaporating. We will use different equations in each section here. If the temperature is changing, we're going to use mc delta T. Okay? This will be mc delta T1. If the temperature is not changing and there's melting, we're going to use an equation m times LF. LF is another constant called melting constant or latent heat of fusion. And it's a given value for each material that is melting. For after melting is finished, keep giving some more heat. I'm gonna use the MC delta T. Of course, I'll have a different delta T here, right? Delta T here, delta T1 would be minus 50 to 0. Delta T3 would be 0 to 100. And then as the evaporation is happening, let's call this Q4. We will have M times the latent heat of evaporation, LV. It will be given to us. Here's a concept question related to this idea here. Let's say I have a drink, and I'm going to put same amount of water at 0 degree. Let's say in this one I put water at 0 degree, okay? And 0 degree. Let's redo that. At 0 centigrade. Cold, right? And I'm going to put ice at 0 centigrade. We all know that we choose to put ice and it will make our drink cold. But now we know why it should be ice. Because if I put ice at 0 degree, first it will melt, right? It will stay at 0 degree, it will melt. It will take some heat from my drink. Q1 from my drink. And then now the ice is changing phase. It's not changing its temperature, but my drink is not changing its phase, so it's changing its temperature. And then heat up to a certain final temperature. That will be the same as my drink. Take some more heat from my temperature. Q2 from my drink. So it will take in this much heat. It will be more if I put just 0 degree water at 0 degree. It will heat up to a certain value, take in some heat, but it will be only the second part of heat taken. Same mass, same value. So this part is only taken from my drink by water at 0 degree, while there is another section taken. So the more heat goes into the melting the ice plus heating up the ice to a common temperature. So that's why ice is better to put in our drinks. Here's another graph showing the same idea. Here we have the heat versus temperature. As heat increases, temperature increases. If I have a solid, for example, until the melting starts, right, temperature increased here. And then as the melting happens, although heat is increasing here, temperature stays constant. So I use this equation. There is melting, so we use LF, latent heat of fusion, or melting coefficient. And then after melting finishes, heat increases, temperature increases. Then we have boiling and evaporating, temperature stays constant, heat increases. So each time we have a phase change, we have ml for calculating the heat. The same here, phase change. If there's no phase change, temperature will be changed in all the other areas. Where there's no phase change, the equation that holds is MC delta T. Here are some values for melting point, solid to liquid temperatures, solid to liquid heat of fusion. Heat of fusion or latent heat of fusion is constant, and it's for either solid to liquid melting or liquid to solid condensing into a solid again. We'll have this constant here, LF. If there is evaporation or gas condensing into liquid, we will use this. So I am heating increasing heat here. I have solid, it melts, becomes liquid, then it boils, becomes gas. I can also go the other way around. I take a gas, take heat away from it, heat decreases until it becomes condensing in the water. I'll use the same equations. Only now my delta T will be hotter the colder, MLV will stay the same, MLF will stay the same. And all equations from gas to solid also holds the same. So inverse reaction is also the same approach. We can calculate how much heat the material loses instead of gains. Simple idea here, just to settle that down. If you heat a substance in an insulated container, is it possible that the temperature of the substance remains the same? Yes. So I have an insulated container. Let's say I have ice. I'm heating it. Give some heat in. If melting, right, temperature can't stay the constant. Delta T is 0, change in temperature. So if there's a phase change, temperature will stay as constant, although we are given heat to system or taken away heat. This one is another logical question. We have silver. Let's say silver, 1 kilogram. It has a heat capacity of 243 joule per kilogram Kelvin. And it has a temperature, I'm going to call this TS, maybe T silver, 100 centigrade degree. And we have water, also 1 kilogram. In a beaker, and it is at 0 degree colder. That's called T water. And the heat capacity of water is large, a lot larger than silver, 4,190 joule per kilogram Kelvin. And we drop this guy into water. Drop. What happens? They will have a heat exchange, right? Let me draw the silver red here. Silver will give some heat to water. Water will take some heat. Right? So this is a give by silver. Water takes it in. Whatever silver gives is equal to whatever water takes, because that's taken from the silver. So we have this idea here, and we can look how much the temperature changes. Calculate it. We can say M1 C1 delta T1 is equal to M2 C2 delta T2. They will reach a final common temperature. This is actually what we will look at in a bit later, called calorimetry. One gives heat, the other takes. What is their final temperature? They will reach to the same final temperature, but water's temperature will be increasing, and silver's temperature will be decreasing. Now, they have the same mass, right? I could think like maybe they will share the same temperature, so it will be like in between 0 degree to 100 degree, right? They will meet in the middle. If I go logical here, I would say if they had the same heat capacity, that would be the case. But water has a lot larger heat capacity, so it will absorb in much more, needed much more heat to have the equal temperature right in the middle for water. So water's high heat capacity will bring the final temperature a little lower than the middle temperature, 50 degrees. So it will be between 0 to 50. It can't be higher than 50. It would be 50 degrees if I calculate from here in the middle, because if they would have the same heat capacity. If same, they would meet at 50 degrees, just the mid temperature. But C2 is significantly the water. Let's call these water and silver. Water. So C2 is larger than C1. It will absorb a lot of heat and it will prevent meeting at 50 degrees. It will lower it down a little bit. Again, I can use this equation. The heat given is always equal to heat taken. Some of them you'll get negative here. Just look at the absolute values. You can calculate the final temperature here. Or one given value, the other one can be found. Another example here to settle and understand the idea of melting and freezing and so on, what we should do, how we should calculate the total heat taken. This one is a very good example for that. A girl eats 45-gram frozen popsicle that was taken out of a -10 centigrade degree freezer. So I have a popsicle at -10. We will pretend this is a pure water, okay, simplified. A girl heats it up. How much energy does her body use to bring the popsicle up to her body temperature? An average body temperature, I should have put here, is 37 degree centigrade. Okay, so she takes that frozen popsicle. First, she'll have to heat it up to 0 degree, right? And then she'll have to melt it at 0 degree. 0 degree. Let's redo that. 0 degree here. And then she will heat up to her body temperature of 37 degrees. So that's the steps here. We have 3 steps or given heat into this popsicle. Heat 1 is given to heat it up from -10 to 0. Heat 2 is given to melt it. And heat 3 is given to heat it up from 0 degree to 37 degree. Here, no temperature change, so heat 2 here is equal, we'll use M times LF, heat of fusion for melting. Here there's a temperature change, delta T1, so Q1 will be MC delta T1. And here there's a temperature change, I'm going to call it delta T3 to agree with Q3. And I'm gonna use Q3 is equal to MC delta T3. Now I'm gonna convert Celsius to Kelvin, right, by saying Celsius plus 273 Kelvin. But I'm gonna take a shortcut here. I know from Celsius to Kelvin, delta T's will not change. So delta T1 will still be 10 Kelvin. Final minus initial, positive. Delta T3 will still be 37 Kelvin. Use those input all, calculate all. Q1, MC delta T1. For C here, that's an important thing that I should have, I'll call this C1, I'll call this C3 to agree with that. Here I have water plus, not here though, I'm sorry, here I have, not water plus, I have ice, right? So I'm gonna use C for ice. I believe it is different than water. I have it here. So I have to use C ice for C1. And that's, let's see here, 2090 excuse me, joule per kilogram Kelvin. And here I have latent heat of fusion for ice melting, and it should be here 3.33. These are all from the tables. Times 10 to 5. This will be joule per Kelvin. And here C3 will be seawater, and that's different than ice, and that's 4,190 joule per kilogram Kelvin. Now I have all my values. Here, again, I'm going to put sea ice. Let's call it C1, sea ice, delta T1, 10 Kelvin. Find this guy. How much was the mass? 45 kilogram. We forgot about that. Mass is equal to 45 not kilogram, gram. Convert to kilogram directly, divide them by 1,000. 1 0 not 2. We all use SI units, remember. So 1 kilogram is equal 1,000 grams. Reminder here. So you will get Q1 to be, let's go back to blue here, 940, oops, 0.5 joules. Q2 mLF for water ice mixture. Put in the values. You will get Q2 to be a large value because this value is large. 14,985 joules. Q3 mC3 delta T3. This will be seawater. Input that there. This guy simply. Delta T3 37 Kelvin. Input that. You will get 6,976.35 joules. What we see here right away is that it's a lot more heat energy given to change the phase than heating up to 0 or from 0 to 37. So that's an interesting thing to notice. Then you will say the total heat given is addition of all these. And you should get, do I have that here? 22,901.85 joules. So that will be on a very involving harder end question involving the heating up to melting point, melting, heating further. Alright. We all know that we have evaporation. Water evaporates from our body, keep us cool. So perspiration is the way of our body to keep us cool. And water here evaporates. We don't have 100 centigrade degree in our face, right? It would burn us. Not good. Actually, water evaporates at lower degree. We can still calculate the heat taken from our body using M times L evaporation, would be LV. But it will be a different value than boiling water, latent fusion of latent heat of evaporation. For example, at 30 degree, latent heat of evaporation is 24 times 25 joule per Kelvin for water from our body versus 100 degree latent heat of evaporation is smaller. So slightly larger for evaporating water at degrees lower than 100. Other than that, it's the same as evaporation, and we can calculate heat taken out of our body using M times LV. Only LV will be slightly different value, larger. We know dogs pants to evaporate water from their tank to feel cooler. Elephants put waters on their body. As water evaporates, they cool off. So that's the idea there. Calorimetry is the quantitative measurement of the heat transfer between the objects. I already mentioned that, although we didn't explicitly calculate, we said we put silver in water and one will be given heat One will be taken here. If we have ice, it will be the other way around. Let's say we have ice here. I think we do because it says heat into ice. So water will be given heat to ice. Let's say water is given Q1 and ice is taking Q2. They should be equal to each other in absolute values. We can calculate their final temperature, because the final temperature will be the same. They will reach to a common temperature, all right, at the end. Depending on the situation, if there's ice melting and so on, we'll have to take into account, right, that as well. So if the ice is melting here, Q1 will go from water. Ice will take in Q2, but that will be taken in some to melt, right, and then reach to a point. You will still calculate that as MLF, then MC delta T, and this will be simply MC delta T, right? So this is given equals to that, but calculating that will be different. So we'll use appropriate equations, and delta T taken as T final minus T initial. Given heat is equal to taken heat. One is plus, one is minus, right? One loses heat, one gains heat. So when we add them, we'll get 0. That's one thing we can use. Or their absolute value is always the same is another thing we can use. All right. This question here is involving that idea. I have a solution, video solution for it. I'm gonna suggest you to solve it, then watch the video and understand it. So I have here an unknown metal. Mass is 200 grams. And its temperature, that would be its initial, maybe the initial one, 90 centigrade. And I have water. T initial T is 20, no, not 20, that's final temperature given, 20 centigrade. A mass of water, I'm going to call these M1, M2 as well, is 50 grams. And we drop this metal in here. Drop. What will happen? One will take heat, one will give heat, right? And who is hotter? Metal is hotter. So metal give heat, Q1, and the water will take it, Q2, right? And you will use Q1 is equal to Q2, absolute value here, to identify the metal. That's what the question is asking. If they reach a final temperature of 27.7 centigrade degree. So you simply say M1 C1 delta T1 is equal to M2 C2 delta T2. Delta T1 for metal, this is metal, we call this metal, this is water. You'll be negative, you ignore the negativity, and delta T is always T final minus T initial. They have the same T final, but different T initial. So you'll say here T final minus T initial 1, here T final minus T initial 2. C1 is the C of water, you know that. Sorry, C2. You know masses, convert to kilograms. C1, you don't know? You find that. Check table to see what it is. So attempt to solve this, find it, check the table and see what it is, and then watch the video. All right, I will see you again soon.